Tar and bitumen are some of the most important, and least appreciated, materials in modern civilization, holding together highways, sealing roofs, waterproofing foundations, and protecting infrastructure that millions of vehicles rely on every day. What looks like simple black sticky liquid is actually the final product of heavy hydrocarbon chemistry, extreme heat processing, vacuum distillation, and careful grading systems designed to create a binder strong enough to survive crushing loads, rain, UV radiation, and temperature swings for years. In everyday language, people call it tar, but the road-building material used today is typically bitumen, a petroleum-based binder produced from heavy crude oil refining. And today on the How Factory, we're going inside modern refineries and asphalt plants to see exactly how tar-like road binders are made, from heavy oil to road-grade bitumen. The history of tar and bitumen goes back thousands of years. Ancient civilizations used naturally occurring bitumen, seeping from the ground as waterproofing for boats, mortar for bricks, and even as an adhesive. The material was prized because it resisted water and could be molded when warm. As cities grew and travel expanded, road builders searched for strong binders that could hold crushed stone together. Early roads used everything from packed gravel to tar-coated stones, but the modern asphalt road system exploded in the 20th century when petroleum refining made bitumen available at industrial scale. Today, road-grade bitumen is engineered with precise viscosity and performance requirements depending on the climate and traffic load. Modern production begins at an oil refinery, a massive industrial complex designed to separate crude oil into useful fractions. Crude oil arrives by pipeline, ship, or rail and is stored in large tanks. It's not a single uniform liquid. It's a mixture of thousands of hydrocarbons ranging from light gases to heavy residues. Bitumen comes from the heaviest portion of crude oil, the part that doesn't evaporate easily and remains after fuels like gasoline and diesel are removed. The first step is atmospheric distillation, the refinery's primary separation process. Crude oil is heated in large furnaces to around 350 to 400 degrees Celsius, and then fed into a tall distillation tower. Inside the tower, hot vapor rises and cools as it climbs. Lighter fractions condense at higher levels, while heavier fractions condense lower down. This creates streams like gasoline, kerosene, diesel, and gas oil, each pulled off at different points. What remains at the bottom is the thickest, heaviest residue, the starting point for bitumen production. This bottom residue still contains valuable components, so it undergoes further separation using vacuum distillation. Vacuum distillation works by lowering pressure inside the tower, allowing heavy oils to boil at lower temperatures without cracking or burning. The residue is reheated and fed into a vacuum tower. Under reduced pressure, more usable gas oils can be extracted, leaving behind an even heavier material known as vacuum residue. This vacuum residue is the base for road-grade bitumen in many refineries. At this stage, the material is extremely thick, nearly solid at room temperature, and it must be carefully engineered to meet road specifications. Not all vacuum residue automatically becomes good bitumen. Refineries adjust bitumen properties using different processes depending on crude oil type and desired performance grade. One method is air blowing, also called oxidation. In air blowing units, hot residue is pumped into reactors while air is injected through the liquid. Oxygen reacts with heavy hydrocarbons, causing them to form larger molecules and increasing stiffness. This process raises the softening point and changes viscosity. Air blowing is commonly used for roofing bitumen and certain industrial grades, and it can also be used to tune road bitumen depending on the market. Temperature, airflow rate, and reaction time are tightly controlled because too much oxidation makes the bitumen brittle, while too little leaves it too soft. For road use, performance must be balanced. Bitumen must be soft enough to flex without cracking in cold weather, but stiff enough to resist rutting and deformation in hot weather under heavy trucks. That's why bitumen is graded carefully. Modern markets use viscosity grading or performance grading systems that classify bitumen based on how it behaves at different temperatures. Refineries continuously test samples for penetration, softening point, viscosity, and temperature susceptibility. Once bitumen meets target specs, it is sent to storage tanks. Bitumen storage tanks are enormous and heated continuously because the product must stay pumpable. Heated coils or external heaters maintain temperatures often between 150 and 200 degrees Celsius. Without heat, bitumen would solidify and become impossible to move. Tanks are insulated and equipped with circulation pumps that keep the product uniform and prevent local overheating. From the refinery, bitumen is shipped to asphalt plants and construction sites by tanker trucks, rail cars, or ships. Transport is a major engineering challenge because bitumen must remain hot enough to flow. Tankers are insulated and some have built-in heating systems. Loading and unloading requires specialized hoses, pumps, and safety equipment because hot bitumen can cause severe burns. At asphalt plants, bitumen becomes the binder in asphalt pavement. Asphalt is not just tar, it is a carefully mixed composite of aggregates and binder. Aggregates include crushed stone, sand, and mineral filler. These materials are delivered to the plant in large piles and stored by size. The plant's job is to dry, heat, mix, and coat aggregates with bitumen to form hot mix asphalt. The process begins with aggregate drying. Cold, damp stone is fed into a rotating drum dryer. Burners heat the drum, driving off moisture. This step is critical because water and bitumen don't mix. Moisture would prevent proper coating and cause weak pavement. Dust collectors capture fine particles and emissions, keeping the plant compliant with environmental rules. Once dried and heated, aggregates are measured into the exact blend required for the asphalt recipe. Different road layers require different gradations. Base layers use larger stones for strength, while surface layers use finer blends for smoothness and grip. Now the hot aggregates enter the mixing section where bitumen is injected. Bitumen is pumped in at controlled temperature and sprayed onto the moving aggregate. High-speed paddles or drum mixing action coats every particle in a thin binder film. The goal is uniform coating without overheating. Too hot and bitumen ages prematurely, becoming brittle. Too cool and coating is incomplete. Plants monitor mix temperature constantly, typically aiming around 150 to 170 degrees Celsius depending on binder type. Many asphalt plants also add modifiers. Polymer-modified bitumen uses additives such as SBS polymers to improve elasticity and rut resistance. Rubberized asphalt may use recycled tire rubber to boost flexibility and reduce noise. Anti-stripping agents can improve adhesion between binder and stone, especially in wet conditions. These modifications help roads last longer under heavy traffic and extreme climates. Once mixed, hot asphalt is stored temporarily in insulated silos, then loaded into trucks for delivery to paving sites. Timing matters because asphalt must stay hot to remain workable. Trucks often have insulated beds to maintain temperature on the way to the road crew. Back at the plant, quality control labs test asphalt samples continuously. They measure binder content, aggregate gradation, air voids, compaction behavior, and performance under temperature stress. Roads fail when asphalt is improperly mixed, poorly compacted, or mismatched to climate. That's why asphalt plants operate like precision factories rather than simple mixers. Environmental controls are also important. Bitumen production and asphalt mixing generate emissions and odors that must be managed. Refineries use scrubbers and controls for sulfur compounds. Asphalt plants use dust filters, vapor capture systems, and strict fuel controls. Modern plants also use reclaimed asphalt pavement, RAP, where old asphalt is crushed and reused, reducing the need for fresh bitumen and stone. Recycling allows roads to be rebuilt with fewer raw materials and lower environmental impact. What makes road-grade bitumen remarkable is how it behaves like a solid and a liquid depending on temperature. It must flow hot, coat stone, then become a tough, flexible binder that resists cracking, deformation, and water damage. That performance is engineered by controlling crude oil fractions, vacuum distillation, oxidation, and precise grading systems. From heavy crude entering towering refinery distillation columns to thick residue becoming refined binder, From heated storage tanks to asphalt plant mixers coating stone at high temperature, the journey of tar is a hidden industrial chain supporting modern transportation. Every smooth highway and city street depends on this black binder, quietly doing its job under constant pressure. And that is exactly how road-grade bitumen is separated, refined, tuned, tested, transported, and mixed into asphalt, transforming heavy oil into the tar-like binder that holds the world's roads together. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and industrial systems that keep civilization moving.